started. Okay, we'll start from current slide. All right, I do have a couple of announcements. Every time I think it's all going to be straightened out soon, hopefully it will be. If you haven't heard yet, I've been having, in the last 2 weeks, miserable car trouble. Finally had to just get rid of the old car, sold it Monday, and I've been in a rental car this week, and we had planned to pick up the new car on Friday, but when my wife, the guy got in touch with her yesterday and said it's ready now. So we're going to drive up this afternoon to Jasper and pick it up. The trouble is he leaves there by 5 or 5:30, so that means I will not have my office hours of 3:15 to 5:15 today. As soon as I get out of differential equations at 3:15, as soon as I can get away, I'm on the road to Birmingham to pick up my wife, because we have to take a vehicle and drive one back, so it have to be 2 people driving. So no office hours today after 3:15, none. Which that means the only time I've got today is my lunch hour from this class is over with, 11:15 to 12:15. Okay. Any questions on anything else? I think after this, hopefully there won't be any more of this mess going on. Any questions? All right, we were talking about strategies for integration, and we were on page 407, section 7.6, and we were just about to hit D. Okay? All right. Sometimes I just skip D because of what it is. Here's what they say D is. The integral, oops, let me get my pen set up. Okay. The integral of e to the x hyperbolic sine of x dx. And I think you probably recall what I think of hyperbolic functions, right? To me, they're hardly worth doing it. If you got them and you have to use them, okay? But what a hyperbolic sine is, and if you don't know this, you can always look it up. I was just going to tell you where to look it up if I can see it quickly. It's not on the front part, so I think it must be on the back part. But I can't swear to that. Let me see. Hyperbolic functions. On the back part of your text, it's about 3 or 4. Is before. Okay, at the very back part you have your integration tables. Before that you have differentiation tables. Before that you have a page that says exponential and logarithmic functions on the top, hyperbolic functions in the middle, and then inverse hyperbolic functions at the bottom. Okay? I really don't want to go there either. But there you see what hyperbolics in the middle, hyperbolic sine is e to the x minus e to the minus x divided by 2. Okay? So how do you integrate that? You don't use hyperbolics. You could, I guess, if you wanted to, but you rewrite it as what it really is. It's the integral of e to the x, and then the hyperbolic sine is e to the x minus e to the minus x, that's the x, my pen's not doing well today, divided by 2 dx. Okay? You rewrite it the way it should have been written in the first place in my mind. Okay? And then pull out the 1/2, the 2 there, and then multiply the rest of it. Okay? E to the x times e to the x is times, not adding. E to the 2x. When you're multiplying same bases, different exponents, keep the base, add the exponents, right? Okay? How about e to the x times a negative e to the minus x. So that's going to be a minus. What's e to the x times e to the minus x? 1. You're absolutely right. dx. I think we can do that integral, can't we? Well, I don't need the integral sign anymore. It's the antiderivative of e to the 2x. Say again? Certainly has an e to the 2x in it. Over 2, right? Okay. Say again?
Oh wait, no, minus x.
Minus x. There it is. Okay. Why mess with the hyperbolic sign? You could have done that by integration by parts if you wanted to. Who would want to? I mean, no. Okay. Far better to do it that way. Well, yeah, okay. I'm sorry. Then they did one more step. They multiplied through e to the 2x over 4 minus x over 2 plus c. We forgot about our plus c, didn't we? Okay. Now, so this all fell under A through D. Do any algebraic simplification possible. Cancel terms and fractions when possible, and then they showed that. Okay, and this was certainly a good algebraic step to do. Don't write hyperbolic sign in there, get it back to its exponential form, and then multiply through. Now, if nothing works there, then look for a potential substitution. Okay? And you know how to substitute. And they do a couple of examples here, so I'm going to, to eliminate this, erase it. Okay? I did. Okay. Here's one. The integral of x squared sine x cubed dx. How would you do that? Ah, very good. Let u equal x cubed. Then du is equal to 3x squared. Is that what I heard? Anything else? Dx. Okay, I thought I heard that. Okay. Now, our original integral doesn't have the 3 in it, so what can we do? Divide it out, but on both sides. Okay. Now this new integral becomes the integral of 1/3 the integral of, because dividing out the 1/3. The du is the x squared part, because we've got the 1/3 out front. Sine of u. Okay? Uh-oh. What's the antiderivative of sine u du? Say again? You may have said it right. What did you say? Hey, it's multiple choice. Okay. Yes, it's negative cosine. So it's minus 1/3 cosine u. Okay? Plus c. Okay? But we didn't really start with u's. We started with x's. So what would the answer be in terms of x's? What would the answer be in terms of x's? There is a minus sign hiding there. Negative 1/3 cosine of x cubed plus c. Okay, hopefully they got that too, did they? They didn't work it out, okay? Not that I can see. Here's another one they do. I think I'll clear this. Are y'all okay with it? Okay. This is a weird looking one. What if we're integrating e to the sine x cosine x dx? How would you do that? Okay, let u equal sine x. Then du is equal to second. Oh, even the sign's right. Okay, cosine x dx. All right. And this is a pretty simple one. What does this become then? If we change our x's to u's, e to the u, du. And what does that become? E to the u. Indefinite integral plus c. But we didn't start with u's, we started with x's, so what's your answer? E to the sine x plus c. Got it. Okay. They didn't carry it out, but that's what you do. Okay. One more like that, or kind of like that, a little bit like that. All right, to erase it? I did. How about this one? The integral of e to the x times the square root of e to the x plus 1 dx. Where would you proceed on this? Okay, what would you substitute? What would you have that be? U, why not? Okay. That u equal e to the x plus 1. Ooh. Yeah. Let's try and let me make sure I wrote it right. Yeah. The plus 1 is not part of x, it's e to the x plus 1. Yeah. Okay, then du is equal to e to the x dx. Okay, so this part's taken care of. All right. So what does this become? Second? Root u. Okay. I'm going to write that as u to the 1/2 power. Okay, that's square root of u. Okay. Isn't it? Yeah. Okay. And what does that become? U to the 3/2 times 2/3 plus c. And what does that become? Second? 2/3, I'm going to put that up front. e to the x plus 1, right? I've got to sneeze something fierce. Sorry. Sorry. Y'all wake up? Okay. To the 3 has power plus c. Now, there's a couple of different ways you could write that, okay? You don't have to change this by any means, but there's a couple ways you could write it. Since you started with radicals, if you wanted to leave it as a radical, that could be 2/3 e to the x plus 1, but the square root of e to the x plus 1 cubed, okay, plus c, or 2/3 the square root of e to the x plus 1 cubed on the outside, plus c. Both of those are the same. You can either take the square root and then cube it, that's what the 3 has, or you can cube this inside the square root and then take the square root. Either one. I like that answer over there the best of all, but your original problem had radicals in it, so if you wanted to write a radical, you could. Not required, and they don't give an answer, so don't sweat it. Okay. So let's do example 1. These were all, what did they call them? Examples, but they weren't numbered examples. So there's a student in my last class came up after the class was over and said, "Can you do anything about the temperature in here?" I said, "No, I can't." She said, "It's freezing." Well, the last class was a room full of people, and I was moving around a lot, not sitting here working on this, but waving my arms a lot, and I didn't even notice it was cold. But as soon as all that body heat left, y'all weren't generating much at all. You're not thinking very hard, are you? Okay. No, I didn't think so. No, I didn't say that. Okay, and now I'm sneezing like crazy, so I wish I could adjust the temperature, but I can't. So here's what example 1 is. Find the integral of x cubed times the square root of 1 plus x squared dx. What would you recommend on this one? Okay, we can certainly do that. The integral, you tell me what to write. Say again? Okay, x cubed times 1 plus x squared to the 1/2 power. Is that what I understood? Yeah. Is that what you meant? Okay.
You still have to substitute it.
Okay, what's your substitution?
Let u equals 1 plus x squared, and then u equals x cubed.
Say again?
Equals x cubed dx.
How did you get that?
So it would basically be 2x, right?
2x? Yeah. Okay. All right. And that's not x cubed dx, is it? Which you were trying to make it, whether it wanted to or not. Okay? It's one's rule. Okay. So what in the world do we do with this? What do we need? Well, number one, we don't want the 2 there, so let's first divide out the 2. So that gets rid of that. But we have an x cubed, not an x dx. Well, the x goes with dx, that leaves us a what? Up front.
1.
Here. you take one of these x's, put to the dx, so you can replace that with du over 2, right? What are you left with here?
X squared.
X squared. But here we have an expression in x squared. Huh?
Yes, we do.
What would that be? Pretty exciting stuff, isn't it?
You gotta change it to what?
Okay.
What do we do now?
New math? I don't think so. I want to find out what x squared is from the line that you already gave me.
Oh,
Oh!
okay.
What is x squared?
-1.
Really? That's sort of hard to do, isn't it? In the real number system. I think he's in imaginary space today. Okay. U minus 1. All right. Let's see what's happening. Huh? You got it? Okay. So now let's take our rewritten form in the old math. Okay. And this will then be the integral of, you're going to have a 1/2 in front. U minus 1. Okay, I already put the 1/2 out. I got the du here. Okay. There's no other meat, no. U to the 1/2. Okay. Right? So we got everything accounted for. 1/2 for the du will be x dx. So one of these x's goes with that. That's the du is x dx. The 1/2 in front, so the 1/2 is here. What's left over was x squared, which is u minus 1, and this part was the square root of this part was u to the 1/2. Right? Is that any better? Yeah, I would say quite a bit. What can you do from there? Second. I'm going to sort of, hopefully this won't be confusing. The binomial here is to a radical. You can't distribute into a radical. But if your radical is a monomial, you can distribute. I don't know if I have them convinced or not. What would you say that is? U to the 3/2 minus u to the 1/2 du. And now can we integrate that? U to the 5/2, is that what I heard? Second, 2/5 u to the 5/2 minus u to the 3/2 times 2/3. Okay? Plus c. Okay. Now, when you distribute the 1/2 across there, then you lose both of these 2's. So you have, so Don't have that anymore. So you have u, which is what? Okay, 1 plus x squared to the 5 halves power over 5 minus 1 plus x squared to the 3 halves power over 3 plus c. Now they may write that as 1/5 and 1/3. You might write it as 1 plus x squared to the 5th power, take the square root of that, or you take the square root of 1 plus x squared and take that to the raise that to the 5th power. There's a lot of different ways you can write the answer. Let's see how they did. They did not too far from what we did. 1 plus x squared to the 5 halves power over 5 minus 1 plus x squared to the 3 halves power over 3 plus c. Good for them. They even got it right. Okay. Make sense? Okay. So even if it doesn't look like it's coming out, use this if you can. If that worked out. If that had been a u squared in front, nah, you couldn't have done the thing. Okay? But, and x to the 4th, nah, I don't think you could have done that. X cubed, because you had an x squared in your u, and a x in your du, yeah, that worked out very nicely. Okay, nose is running now. Sorry. All right, let's go to example 2. All right, to erase? All right. Example 2, evaluate this. I don't even want to write this, okay? dx, hopefully that is the 10 o'clock siren on Wednesday, right? Yes, okay, we're all right. And this is the square root of x plus 1. I think I wrote it right. Huh? What'd you say? Kinda. Okay. Now, how would you begin that? Say again? Okay. I heard a let u equal something. What did you say it was? I thought that's what I heard, did I? Let u equal x? X plus 1? I don't even see that in the problem. How about square root of x plus 1? Or maybe just square root of x. I don't know. We may have to fish around a little here. X plus 1 won't work because there's not an x plus 1 anywhere in there. But square root of x plus 1 might work. Okay? What would you do from there? Okay, then du. Well, they sure are blowing it a lot today, aren't they? Okay. Usually hear it that goes this long. What would that be? Okay. What does d mean? Oh, okay. New math. Okay. 1/2 x to the negative 1/2. Okay. What else? dx. Right? Now, now, second. Okay, I'm still not convinced it's going to help us. Okay, so let's do a 2 du is equal to 1 over square root of x dx. Because it's x to the minus 1/2, right? And right now I'm not seeing that. Well, let's see.
If we would let u just equal to the square root of x.
Say that again.
If we didn't do the plus 1, could we kind of do what we just did on line 1?
Okay. Well then, if you didn't do that, this part's still the same, right? Okay. Okay. All right. And it said our first inclination that it says it won't work, and that's what we just sort of discovered. Instead, let's try a different substitution. Actually, that's the one I did try. Okay. Ha. Okay. We were right in our substitution. What we were wrong in is to take the du too soon. Okay. We might come back and do it, but right now let's do the other. Then this implies that the square root of x is equal to u minus 1, right? Okay. And then that makes x equal u minus 1 squared. Right? Okay. Now here's why you do this. Because you see that dx has not got anything else with it, it's just dx. So at this point you can take dx, and what do you get? Huh? Differentiate that side, what do you get? Okay. You got what x is, right? Okay. Now figure out what dx is. Differentiate this. That's what d means. Take a derivative of it. What does that give you? If you're taking the derivative of that, what is the derivative of that? 2 times u minus 1, right? 2 times u minus 1 to the first power. du. Right? Okay. Now, that's going to be our dx now. Okay? And let's see what we've got now. We've got the integral of, I'm going to take the 2 on the outside, u minus 1 dx, right? That's your, I'm sorry, du, right? Okay, that's what dx is. The 2's on the outside, okay? And then what we've got here is u over u to the 1/2 power, right? I don't like writing it like that, but I already had everything else in place right there. Because you see, this is the square root of u, right? You see it? But it's in the denominator, okay? This is how I wish I had thought to do it. 2 times the integral of u to the minus 1/2 times u minus 1 du. Right? You just pull that up there and make it u to the minus 1/2, u minus 1 du. You see that? Okay. What can we do there? Looks an awful lot like what we had before, doesn't it? Not quite, but similar. So what do we do? What? Okay. Nope. Distribute. Okay. What does that give us? Say again? Okay. That's okay. This is u to the 1, right? That u, and that 1 is 2/2, isn't it? Okay. So u to the negative 1/2 times u to the positive 2/2 is u to the, keep the base, add the exponents. Got it. U to the 1/2 minus, I'll distribute the other one, negative 1/2 du. Okay? That's 2. Can we do that? Sorry. First integration. U to the 3/2 times 2/3 minus u to the 1/2 height, okay. Okay. Plus c, right? All right. Now let's see what this turned out being. The first one is 4/3. Okay. U is square root of x plus 1. So that would be, I want to write that as x to the 1/2 plus 1. Is that okay? I just don't like radicals that much. Okay. To the 3/2 power. Right? That's what your u was, right? Minus 2 times 2 is 4 times x to the 1/2 plus 1 to the 1/2 power. Okay? That was your u plus c. I think, therefore I am, that's, where in the world is, oh, there it is. Okay. So let's see what we got. 4/3 square root of x, they wrote the radical, I guess I should have to, plus 1 to the 3/2 power minus 4 times the square root of x plus 1 to the 1/2 power plus c. Yes. Okay, that was a little on the tricky side, because you couldn't get from doing u equal then doing a du. So isolate the x in terms of u, and then do a dx, and that came out a lot cleaner. Okay? A trick. If it works several times, call it a method. Okay. Now, those were some pretty complicated substitutions. When substitution doesn't look like it's going to work, we might try integration by parts. Okay? Y'all remember how that goes, right? Here are just a few hints on integration by parts. If you have an integral, which is x to the nth power, times some other function, f of x, dx, okay? This is the classic one to let be u, and that be your v. Remember? U dv, right? What you want then is that when you integrate that dv, you want it to not get any worse. This, when you differentiate it, it's going to get better and better and better, as long as then it's positive. But that one, you don't want to get any worse. So what would be potential functions for the f? This is good to use as long as f is one of these functions. Okay? Sine x, because that doesn't get any worse when you integrate it. You get plus or minus signs and cosines, but it just goes back and forth, right? Or cosine x, that will work fine. It just goes back and forth, plus and minus, and sine x. E to the x is a great one. Okay? I lost my place here. They show hyperbolic sines and hyperbolic cosine. Just use the e's, okay? We already said e to the x's, okay? Or you can use those if you want to. Secant squared x will work okay, because that becomes a tangent x, okay? And I believe cosecant squared will probably work well too. Yes, cosecant squared x, because that will become a cotangent, okay? And also the x to the n can be replaced with a more complicated polynomial, but you keep differentiating polynomials, they get simpler and simpler. You integrate those and they don't get any worse. Okay. Now, here's kind of an example of that. Okay. What if you had the integral of e to the x sine x dx? Okay. Now, on this one, both of those would be good for your dv's. Either of them would be good for the dv. And they're not going to get any simpler on the u, let u equal. So, what are you going to do on something like that? Repeat it. And either the second or the third or the fourth time through, you're going to wind up with something you started with. And if you get that, then you can do it. So let's do this one. And you choose which you want to be what. Okay? Which you want to be your u and which you want to be the v. dv. I really don't care much. It doesn't really matter. The dx is going to go with the dv. You just choose which function you're going to go with what. Let u equal what? E to the x. Is that what you said? Huh? I was afraid you did. Okay. Okay, that makes dv be sine x dx. I probably would have done it the other way, but it's fine. It's perfectly fine, sort of. Then, what do you do here? du is equal to e to the x dx, and v is equal to, this is why I wouldn't have done it this way, cosine x. Is that right?
Oh, wait, yes. Okay, so it'd be negative.
Negative cosine x. Good pickup there. Okay. Yes. Okay. Now, where do you go from there? Integration by parts says what? uv, which is minus e to the x cosine x. It's usually a minus here, but since you're going to have a minus there, that's going to make it a plus your bottom line here. The integral of e to the x cosine x dx. Okay? Whatever's at the bottom. Okay? Now, we haven't gotten any better. We've got almost the same thing we had before, except it's a cosine. So guess what we do this time? You're supposed to guess, huh? Do it again. Is that what you said? Yes, do it again. First and 10, do it again. Go team, go. Okay, now. And by the way, UAB won their first away game last weekend, didn't they? Huh? Yeah. And that's the first one they won away from home. They've won all their home games so far. That's the first road game they won. So good for them. Okay. What's that?
The band
They did do? Yeah. Oh, that's it. Okay, the band's the lucky thing. See, that's why baseball, y'all need a band. Okay. All right, so what are we going to do here? Let u equal, you better do the same way you did before. Don't reverse them now, because then you'll just undo what you just did. And dv is equal to cosine x dx. Keep the d's with the d's. Okay, then got it. And v is equal to, yes, and we got the sign right that time, didn't we? Okay. What's that? What? Yeah, dv, yeah. When you do an integration by part, you let one part be a u and the other be a dv. And then you undo, you differentiate this and integrate that. And then you do, huh? Yes. And that's why it came out positive. Right? Wait. Yeah. Right. Because derivative of sine is cosine. Antiderivative of cosine is sine. Okay? So then what we put down is the u. So let's get where we were. We already had the minus e to the x cosine x. And now we have a plus e to the x sine x. And now we have a minus the bottom line here, and this is an integral of e to the x sine x dx. Does that help us any? Well, it sort of does, because this is exactly what we had to start with. So that thing there is equal to this thing here, right? So I'm going to write that down, okay? I just don't have a lot of room. The integral of e to the x sine x dx is equal to, I'm going to write the e to the x sine x first. E to the x sine x, that's the sine x, it's the ugly sine x, minus e to the x cosine x, minus the integral of e to the x sine x dx. By that, we had this thing is equal to that thing, right? But, what we can do is add this integral to both sides. E to the x sine x dx. Add it over here. E to the x sine x dx. And now we've got two of them. 2 times the integral of e to the x sine x dx is equal to e to the x sine x minus e to the x cosine x, and then divide by 2, and you've got what that original integral was. Without ever really doing it, we did it, okay? We just subtracted it, added it to both sides, and that gave us our answer. That is a 2 there. It's a very ugly 2. Okay? Okay. Now, I think if I were writing this, I'd write it as e to the x over 2, or 1/2 e to the x times sine x minus cosine x. Okay, something like that. Oh, plus c. Okay, at some point you got to get a plus c in there. Okay? Did they actually do it, or did they just blah, blah, blah it? Okay, here's how they wrote it. I don't know why. They wrote the 1/2 in front. I did e to the x in front, but they put just the 1/2 in front. They led with the negative, which was minus e to the x cosine x, which we have, plus e to the x sine x, which we have, plus c. That's not a very elegant way to write the answer, but they did it that way. I like mine better. But if this had been using good old WebAssign, they would have only wanted one answer, and they would have said all the others are wrong, even though they wouldn't be wrong. All right. I love WebAssign, don't you? All right. All right, to erase this one? Okay. Let's do number C. Although we usually apply it to a product, integration by parts also sometimes works on single functions, such as the integral of log x dx. Okay? How in the world would that work? I don't know how to do it otherwise. Well, if you need a u and a dv, that's what you need for integration by part. U equals something and dv equals something. What does dv better be? The dx. It has no choice. It has to be the dx. What does that leave the u to be? Log x. That's the only choice you have. Okay? Then, what do we do next? du is equal to derivative of log x. It's not an exponential. Oh man, thinking makes my head hurt. Okay. What's that? 1 over x. One other little thing. one other little thing, dx, okay. And guess what d is then? X, all right, I like it. And then what do you do from here? U times v, which is, so this is actually equal to x log x, right? U times v, minus the integral of the bottom line. And what's that? Second? And what is x over x? Second? Okay, multiple choice again. I love them. Okay. X squared over x would be x. X over x would be 1. Right? So that would just be minus the integral of. Yeah. And I think we can do that integral, can't we? So this would be x log x, antiderivative of dx. X plus c. Pretty nifty, huh? And that is a very elegant way to write the answer too. They didn't give you the answer, they just said that's what it is. All right. Now, I don't recall that we did this one, the integral of inverse tangent. But they said do the same thing. So then you would let u be this, dv be that, and then you have to look up and see what the derivative of inverse tangent is. And it's going to be something, okay? And then that would just be a v, and you just go from there. It's not going to be quite as simple as this one was, okay? So that's one way to go. In fact, it may be the only way to go. Do you want to actually do that, or do you want to move on? I was hoping you'd say that. All right, the other one similar to that is inverse sine. X dx. Same thing. Let u equal inverse sine of x, dv equal dx, d is equal to x, and du is whatever the derivative of the inverse sine is, which is something. You can look it up and see, and things will pan out, but it's a fair amount of work. So that's about the only way to do those, unless you can find them in a table, which I like. I think maybe the option of choice, right? Okay, and I think you usually can find those there. Okay. All right. Now, number 4 says, consider the form of the integral. Does it fall into one of the categories for which we have a technique? The first one is it a trigonometric integral? What are the things you look for to make a trigonometric integral? Okay, that's what you're going to be substituting, but, okay, I'm sorry. Trigonometric integral, yeah, is going to be sines and cosines. It could be other things as well, but raise the different powers, and generally, get up at a table, okay? That's usually the best way to do those, okay? There are techniques, and fine, we can go, tangents and secants go together well. Usually we don't use cotangents and cosecants. They would go together well, but they're a mess, so that's that. Okay, so that's your trigonometric integrals. A lot of times just go to a table for those. The B part here says, does the integrand contain any of the following? The square root of a squared minus u squared, or is it x squared? Yeah, no, well, no, they put x squared for this one, and they put, no, they don't, okay. Yeah. The square root of x squared minus a squared, or the square root of, do they put one that doesn't really, x squared plus Now, this could be in the numerator, denominator, anywhere. What would you use for those forms? Second? I can't make out what you're saying. The chart. You mean look it up in the table? Okay. Huh? The one that we wrote. I don't remember writing a chart. I guess we did. Okay, all right. But this is these are trig substitutions. In this kind, you let x equal a sine theta. This one's let x equal a secant theta. This is let x equal a tangent theta. How to remember those? Think of your Pythagorean identities. Sine is cosine squared is 1 minus sine squared. So that looks a lot like that. Secant squared is tangent squared minus 1. It looks a lot like that. And tangent squared plus 1 is secant squared. So that's the one. I mean, tangent squared is secant squared minus 1, and secant squared is tangent squared plus 1. So this will be a tangent, that will be a secant, that will be a sine. And the a just goes with that. A sine theta, a secant theta, a tangent theta. If you didn't have a square here, then it would be the square root of a sine theta, square root of a secant theta, square root of a. So that's what we do with those. Okay. So let's do example 3. All right. Evaluate this. The integral of x squared plus 16 raised to the 3 power dx. What would you do? Secant's got the minus sign. Tangent, yes. Okay? So now this is a substitution, but it's not an old kind of substitution, it's a trig substitution. The old kind, you let u be something of x. This one, you let x be something, and usually since it's trig, you do a theta. So let x equal, and what were you going to say it was? Four tangent theta. Okay? Good choice. Okay? Now you got a couple of thens you can do. So take me to town on the thens. You can go either direction here. What you want to do first. Second? Okay, go down. Moses, okay. What does that give you? Okay, you're going this way. All right, that's fine. I usually do it this way if we're doing this way. X squared equal. Second, 16. Tangent squared theta. Okay. here you have x squared plus 16, so you could do add 16 here and add 16 there, right? Okay. And then what could you do? Second? I can't hear you.
Is that x to the 18th power?
No. Okay, no it isn't. Okay. Maybe I shouldn't have written it like that. Okay. It was an x squared, and then you added 16 to it. So it would look like that. And that's not x to the 18th power. Okay. And then what can you do to that? Both terms. Factor out of 16. Okay. So let's factor out of 16. And what are you left with? Right? Okay, what do we do with that? That is a secant squared theta. Exactly. Exactly. Okay? Now, there's one other thing we do. Well, actually, a couple of things we could do. Okay? Because this thing here, this x squared plus 16, is raised to the 3/2 power. That would mean we could raise this thing. If then we raise this to the 3/2 power, that means this is being raised to the 3/2 power. What I would like to do first is take the square root of it. What's the square root of that thing? 4. Secant theta, right? But then you're going to cube that, which would be 64 secant cubed theta. Right? Agreed? Okay. All right. So we've taken care of that. This thing right here, this whole thing, is 64 secant cubed theta. That's this part of it. Now let's do the dx. What is dx? It would be what? Tangent something theta? Cube theta. How did you get that? You're taking the derivative of that.
So it would be 2 tangent 1/2.
Okay. 4 secant squared theta. The derivative of tangent is secant squared. And just the 4 is there. You need one other little thing here. Huh? What? D theta. Exactly. All right. So now let's rewrite our integral. This thing here, this entire thing here was 64. I'm going to pull the 64 on the outside. And since I'm going to have a 4, 2, 4 times 64 is 258. No, 256. 256 goes on the outside. I may want to bring some back later. But this thing would then be secant cubed theta, and this is secant squared theta, so that's secant to the 5th theta d theta. Do you see that? Yea or nay? Got it? Okay, and how would you handle that? Huh?
Would it be secant 6?
Say again?
Would it go secant 6 theta?
That's what it is. Oh, you mean 6? Is that what you said?
Yeah.
Then you would need a d theta, d secant in there somewhere, which is secant tangent. So you got what I would do is look up in a table, okay? Frankly, okay? And I know that one is. Whether that one's in a table or not, I'm not sure. This is, I know is in a table. It better be in a table. Let's go to the back and see if it is. You can work it out, I mean, but it's long and lots of fraught with potential hazards. Yeah, you have in the back of your book, number 48 is the integral of secant to the nth u du. We've got theta d theta, okay? And you just start working away at it, and you get the answer. So let's start working away at it, okay? So this is going to be a 256, okay? I'll lose my place if I don't watch it here. $256 times 1 over what? Y'all got the back of the book? 5 minus 1, which would be 4, right? What follows that? Tangent theta cube theta, perfect, plus second 3 over 4. Now I have an integral coming up there that I don't have room for. And what would that be? Secant to cube theta d theta. Okay? But if you look over to number 42, you don't have it? You don't have secant cube theta d theta?
I'll go to 40 and 43.
What's that? You don't? Okay. You don't have 41 and 42? Okay, too bad. I have. No. Okay. The secant cube theta taken right out of here is, and this is multiplied by 3/4. So this thing right here, I'm going to put it in bracket here, this is equal to 1/2 secant theta tangent theta plus 1/2 the log of absolute value secant theta plus tangent theta okay, plus c. All right. So it's hard enough with the table. I can't imagine what it would be out without the table. I hope I can afford to erase this with impunity. And let's see what we got. All right.
Is all of that at the end, only all that, just equals secant?
That's just a secant cube. That bottom line is a secant cube. So you got 3/4 times that. So what I'll do is write my 3/4 in front of here. This goes here. Okay. So 4 will go into 256 64 times, right? Yeah. So that's 64 tangent theta secant cube theta, okay, plus the 4 will go into that 64 times, but multiply 64 by 3, and you get 192, I believe it is. 192. Whoops. And I'll divide that by 2, though, because of the 1/2 here. So let me go and take care of that, too. That would be... goodness. All right. So in other words, that's going to be 1/8. 8 will go into 256. 3, yeah, 32 times. Okay. Yeah. 32 times secant theta tangent theta plus 32 times the log of absolute value secant theta plus tangent theta plus c. Okay. That's what I think the answer is. Let's go back and see what they've got here. Oh my goodness. Oh. Okay. What's that? Okay. Well, we haven't gone back. Okay, we got to go back. Okay, you can't go back again, Thomas Wolfe said. We got to go, these were in thetas. We need to get it in terms of x's.
They have, instead of 32, they have 96.
Oh, they do have thetas, don't they? Okay, there they have the thetas. Okay, 64 tangent theta, secant cube theta, but they have plus 96. You're right.
It'd be 192, and 192 divided by 2 is 96.
Oh, I forgot to multiply by 3. I just did 1/4. Okay, 3 times 32 is 96. Yeah, both of those are 96. Yeah, because I just did 1/4. I forgot to multiply by 3. So 96 tangent theta secant theta plus 96 log of absolute value secant theta plus tangent theta plus c. Okay? But we want the answers in terms of x's. Okay? All right. So here we go with the x's. I'm going to erase this at the bottom because I just don't have room for it anymore. I'll erase these and make the 96 is real. Okay? And this is the last part. When these trig substitutions, you really need to get back to the variable in question. And usually it's not too bad. Usually I say it's not too bad. Okay. Let's see how bad it is this time. Here's where we go. X is equal to 4 tangent theta. Draw your little triangle. Okay. So tangent theta, if this is your theta, tangent theta is what? X divided by 4, right? So it makes x the opposite and 4 the adjacent, right? That makes the hypotenuse the square root of x squared plus 16, right? Which is exactly what we had in there, right? Now, let's plug and chug here. 64 times tangent theta. We already know what tangent theta is. That's x over 4. Right? Secant cubed theta. Okay? Well, your secant theta is hypotenuse over adjacent, right? Okay? So your hypotenuse is the square root the square root of x squared plus 16 over 4. Okay, that's what secant theta is, but we got secant cubed theta, so you're going to cube that. Okay? Plus 96 times secant theta, which is the square root of x squared plus 16 over 4, times tangent theta, which is x over 4, plus 96 times the log of absolute value. Secant theta is the square root of x squared plus 16 over 4 plus x over 4 plus c. Okay? Now, 4 cubed is 64, so that's going to wipe out the 64 here, that 4 cubed here altogether. So this gives you 1/4 x times, I want to write it like this, x squared plus 16 to the 3/2 power. Okay? All right with that? Because that thing was cubed. It's the square root cubed, so that's that. Okay. Plus, okay, and here we have denominator totals to 16. 16 will go into 96, I think 6 times, won't it? It's 96 divided by 16, 6 times, okay? And this will just be 6x times, I'm mixing my radicals and things, but I'll just leave it like that, x squared plus 16, okay? Plus, and this, there's not much you can do with it, I don't think. Let's see if they do anything else with it. I hope not. Will they do something with it? I think I've botched something up, but I haven't figured out what it is yet. I'll come back to that in a minute. Yeah, they leave it 96 times the log. Now, they write it as x squared plus 16 to the 1/2. What did they do with their 4, though? I'm not sure on that. The plus x over 4, I've got that. And the plus c I've got. But how did they...
They don't have a 4 on any of them.
And I'm not sure the secant theta is the square root of x squared plus 16 over 4. It's hypotenuse over adjacent. So how did they leave that off? Because they say, you can see it up above, secant theta is the square root of 6, x squared plus 16 divided by 4. Yeah, so when they plugged in, they did 64 times x over 4, that's the tangent theta, okay? And then they left off the over 4 in the secant theta. And I do not see how they did that. So I'm not sure I buy theirs. because we got the same answer they did in the thetas, but when they plugged in secant, they left off those 4's in the denominators of secants. And I don't think you can do that. Okay. So I'm going to leave that alone. Okay. I just think they're wrong, but I can't prove it now. Okay. Okay, if the integral, because this is the first time they've added this section in, I'm not sure they proved it very well. If the integral contains an expression of ax squared, the square root of ax squared plus bx plus c, complete the square first and then continue. Okay, the c part then. Okay, is it a rational function, p over q, for polynomials p and q? If so, we can apply the method of partial fractions, which we just recently completed, and y'all enjoyed doing so much, I remember. So let's do that one. Do we have time? I think so. Let's try it. Let's do example 4. Find the integral of x squared plus 2x plus 10 divided by x squared plus x minus 6 dx. How would you proceed? How would you proceed? Second? Okay, you certainly can factor the bottom. And what that factor is? X plus 3 times x minus 2. Certainly that is going to be helpful and useful later. Okay? Anything else? No. Okay, I did the same thing. I said, can we factor the top? No, it's going to be x plus plus. There's no way that 5 and 2 or anything else is going to add 2. So no, it will not factor. Good try, though. Always worth a look. What else do we have to do, though? You can only use integration by parts if what's true. Yes, the degree of the numerator is less than the degree of the denominator. Is it? No, it's the same. So what have we got to do first? All right, let's do it. Okay, how? Second? What does that long horizontal line mean anyway? Divide. Yeah, we're going to have to divide it. Long division, too. Oh, you're hoping to be able to leave, aren't you? Okay, let's do our long division. What goes on the outside? Yep, and on the inside? Okay. So x squared will go into x squared how many times? 1. And then we do what? Multiply. X squared plus x minus 6. And then I like to change signs and add. Make that minus, plus at the end, and minus in the middle. Okay? And add, and what do you get? The x squareds go out. You left with the x plus 16. Right? Now, so rewrite that integral as the integral of dx. That's 1 dx plus the integral of x plus 16 over, and now is where the factoring comes in handy, x plus 3 times x minus 2 dx. Right? See what we did? The quotient goes in the first integral, and then the rational fraction denominator goes into the second part. X plus 16 over the divisor, but let's write it in factored form. So that's why factoring was a good idea. We didn't need it right then, we need it here. So, can you do the first integral? X. Okay? All right. Plus. Now, what do we do here? Yes, the AB stuff. Okay. X plus 16 over x plus 3 times x minus 2 is equal to, what did you call it? A over x plus 3 plus b over x minus 2. Now what? Okay, multiply everything on both sides by that denominator. So that'll be x plus 3 times x plus or minus 2. This will be times x plus 3 times x minus 2. And this will be times x plus 3 times x minus 2. All right. I'm going to jump down here. The x plus 3, x minus 2's go out here. So you have that x plus 16 is equal to, here your x plus 3's go out, a times x minus 2 plus b times, and here the x minus 2's go out, x plus 3. And now what? That x equal 2. Okay, and what would the left-hand side become? 18 is equal to, second, 5b. Oh, I don't like this much at all, do you? So b is equal to 18/5, right? Not 5/18, right? Got it? Ooh, a big boo kiss. Let me make sure I haven't done something stupid. Nope, it was right. Okay, next. Let what? X equal -3. And what does the left-hand side become? 13. I like that a lot, yes. -5a. So therefore a is -13/5. That looks like fun too. And that's exactly what you got. Okay? Now, that said, this new integral here is going to be -13/5. Okay, let me do some changing here. Okay. The x is from the first part, so it's going to be -13/5. That's the a part. Dx over x plus 3, right? Plus 18/5 times the integral of dx over x minus 2. All right? Really not going to be too bad, except for those strange-looking coefficients. But what does this become? The final answer is x minus 13/5. I think both of them 5s. Yeah. Yes, they are. Okay. What's the integral of dx over x plus 3? Log of x plus 3 plus 18/5 log of absolute value x minus 2, and then plus c. All right, that I hope is how they leave their answer. X minus 13/5 log x plus 3, good for them, plus 18/5 log x minus 2, good for them, plus c. Yes. Okay. Oh, now they say use an integral table. I thought we had been doing that. Okay. We had on some of them. That's where we'll start next time. Okay. This is taking longer than I had planned for it to. These are not trivial. Okay. So we'll start there. And we just got 3 more examples to go. Okay. We'll pick up and go from there. Homework exercises here. You can do any of the odds 1 through 9. And I'd say any of the odds 11 through probably 11 through 57, though 41, 43 lend me a little bit of pause there. And if you don't want to do all those, you don't have to. You can wait until we do a few more. Okay? Good deal. Today is Wednesday already, isn't it? Yeah. Have a good weekend. Working math will make it good, right? Yes, good deal. All right, let's end this.